So let us go for the next topics. Next topics are complex numbers, so the first section is an introduction. So I guess most of you already know complex numbers, and the main idea I want to stress in this introduction, what is the main idea about the complex number? The main idea is the introduction of a symbol. Which is I, the imaginary unit, and of an algebraic rule, that is I squared equals -1. Of course, I cannot be considered as a real number. I is not a real number. Since for every real number x, one has that x squared is not smaller than 0. Okay, it's a non-negative number. Then extend all algebraic rules. Extend all algebraic rules to I, and then consider numbers or better symbols of the type x plus iy, where x and y are real numbers. X is called real part of x plus iy. Y is called the imaginary part of x plus y plus iy, and then use ordinary properties, so commutative, distributive, associative, of sum and product, so of operations of between real numbers. These numbers here, these symbols here, are called complex numbers. Okay? This is the main idea. I will introduce it in a better way later. And so let me just give you some motivation . There is a historical motivation first. You consider just a third degree equation So of the type x cube plus r x squared plus p x plus q equal to 0. And of course, you can immediately see that this equation has at least one real solution, because for certain values, first of all, it goes to minus infinity when x goes to minus infinity, to plus infinity when x goes to plus infinity. This is a function f. So since the function is polynomial, it is continuous, so sooner or later it has to cross somewhere the real axis. But according to the choice of coefficients, there can be another possibility. So we can have 3 solutions, not 2, because the function has to start from minus infinity and end up at plus infinity. So it must have an even number of crossing with the x-axis. So this equation has either 1 or 3 solutions. Another question is whether there is a closed formula for the solutions, for the real solutions. So let me here stress the fact that they are real. Like for the second degree equations, and the answer is yes, there are formula. There are closed formulas for the solutions of such equations, and they are known as Cardano's formulas. It was an Italian scientist of the 16th century. He was really a great mathematician. He invented not only complex numbers without naming them that way, he also gave the basis of the probability theory. And so such formulas are extremely complicated. I don't want to write them because I don't remember. Then nobody, at least nobody among the people that I know, can write them by heart, but they are extremely complicated. It is very difficult to write this word. Extremely complicated. But the important fact is that in such formulas, there is the appearance of the square root of a negative number. Then when the solution is real, then this square root cancel each other, and then everything at the end is real. But in the formula there is this appearance. Of course, this was extremely difficult to name and to consider at the age of Cardano, because at that age the idea of mathematics was quite linked to magic, to the essence of things, and so on and so on. And it was not a free creation, so people did not feel really free to understand, to name things, and to consider things. They were strange things. Consider like the Pythagorean, they were very scared. of the square root of 2, and Cardano and the others, people of his age, were very scared of a square root of a negative number. So, but now we feel free to define symbol and to introduce algebraic rules, and so it is quite natural for us. But we should not forget the history and the fact that we had to overcome many way of thinking, many way of seeing things, and probably in the future mathematicians will be able to overcome some blocks, some psychological and cultural blocks that we have, and we don't see them. Of course, Cardano did not see that it was a sort of historical, cultural, psychological hindrance that he met, and so it is the same for us in the future probably. However, this is the first historical reason for introducing the complex numbers, and the second is theoretical from the point of view of mathematics and also aesthetic, I would say. So also an elegance of the theorem, and the problem was to provide solutions to every equation, in particular to simple equation like x squared plus 1 is equal to 0. Of course, this has no solution in the realm of the reals, but we can introduce by hand the symbols for solutions of this equation. And in particular, this was accomplished because we will see there is the fundamental theorem of algebra that says that every equation with one unknown, then real, and not only real, also complex coefficient, has exactly as many solutions as is the degree of the equation. Of course, some solution can coincide, but so this problem of provide solution to equation that do not have solutions in the realm of the reals is completely solved by introducing the complex numbers. And the last one is you won't believe it, probably. This is not very well considered in mathematical books because mathematicians don't know the physics, but there is also a physical, very important motivation that is linked to quantum mechanics. So the mathematical formalism of quantum mechanics really requires the introduction of the complex numbers. Indeed, quantum mechanics is ruled by a fundamental equation which is Schroedinger equation. Probably you already met Schroedinger equation when studying chemistry, but probably you really did not see the true Schroedinger equation, but only its so-called time-independent version. And the Schroedinger equation, so this is the true Schrödinger equation, so-called the time-dependent, is the following: I dt. Then there is the unknown. The unknown is a function, and the function is usually called psi, and is called the wave function. Is equal to what? Minus dx squared plus dy squared plus dz squared. We are in the three-dimensional space, and then again psi plus, and then there can be a term which is called potential, and so. So All of that, all of those here in this Schrödinger equation are new symbols for you, but it is quite easy to understand. So psi x, y, z, t. This is called the wave function of the system, of the physical system you are considering, which is a quantum mechanical system. And it is not a function like those we introduced here, because it is not dependent only on x. Okay, so it is not dependent only on one variable, but there are three space variables. Of course, in true problems you can have less than three or more than three. Okay? But in this example. And then there is a time variable that says how the system, how the wave function evolves in time, changes in time. So this psi is the unknown of the problem. So it is an equation where the unknown is a function. Okay? Now the other symbols. What I called dt, and d here is not a true d, but it is a sort of the soft d, dt, is also written as d, dt, and it is called the partial derivative with respect to the time variable. So what does it mean? It means that d dt psi x y t z, there is also z in this example, y z t is nothing but the limit for t prime going to t of psi x y z t prime minus psi x y z t, and here t prime minus t. So you see, this is a derivative, but the derivative is only on one variable. So the three spatial variables here are the same, are fixed. What is changing is only the time variable. Okay, this is the idea of partial derivative. Okay, all variables except one are frozen. Only one variable is changing, and so I am considering how the function psi changes when this single time variable changes. And the same is for the x variable. Is here for the x variable, so here we have the x, and here we have x prime going to x, and so let me cancel this prime and put the prime here, and here a denominator x prime minus x. So, and this is the partial derivative with respect to the space variable x, and so on and so on. But this is not the point I want to stress. The point I want to stress is the fact that here there is the I. Okay? For our purposes today, I don't want to teach you analysis 2, at least not now, but I want to stress that there is an I. So the imaginary unit is present in the equation, and this makes the recourse to complex number unavoidable okay, so in order to describe the physical state of a quantum system, you have to use complex number. This is extremely strange, but there is a physical phenomenon, a physical, which is associated to the use of complex number, so described by complex number. Let me be more precise with sort of philosophical epistemological words. There is a physical phenomenon described by complex numbers, and this is the quantum interference. Which is very important. Okay, I don't want to explain that. It is an interference like for the waves, for the light, but it does not concern waves, light, and whatever we are used to think of. It concerns probability. There is a strange interference of probability, and this is related to the use of the complex numbers. Okay, so here we are really forced to do that. So when you will study electromagnetic field, you will see that there is a way of representing also electromagnetic fields through the use of complex numbers. You say that there is the electric field and the magnetic field, and then you describe electromagnetic field like the electric field plus I, imaginary unit, B. But this is not the same thing. This is just an artificial way to represent electromagnetic fields. It is comfortable and so on, but it is artificial. When you study quantum mechanics, it is not artificial. It is really ontologically included in quantum mechanics. Okay, so this is a very, very, very important fact. And it is not really stressed on mathematical analysis books. Of course, when quantum mechanics was introduced, nowadays it's more or less 1 century ago, because the paper by Max Planck was written exactly at the beginning of the 20th century. It was 1900 precisely. Then in the 20s of the 20th century, there was the formalization of quantum mechanics, and in particular the 4 papers by Erwin Schrödinger that introduced the Schroedinger equation. And then this equation was criticized because it bared the presence of I, so of complex numbers, and so what is the physical meaning of complex numbers? And there was a huge discussion. But at the end, so I want to write this. What is the physical meaning of complex numbers? This is a very deep and very important question, and it is this sort of question that you approach and you want to find the answer to the question, you don't find the answer, and then you go forward and forward and forward. After many years, you keep on using complex number without really understanding what is the physical meaning. And so you can give many answers, and so let me give you a practical answer. And the idea is that you can use whatever mathematical tool you need in order to describe reality. as far as it works. There is a beautiful movie by Woody Allen, which is called Whatever Works. It is not about mathematics, it is not about physics, it is about love, but the main character is a physicist, a theoretical physicist, so there is some links. And okay, and I want to tell you another thing. So the same can be said, the same question can be drawn when talking about real numbers. And talking about the revolution, as Tracy Chapman sang, talking about real numbers. And so, what is the answer here? The answer is that real numbers are as abstract, are as complex numbers are. Because in physics, you don't use real numbers. When you perform a measurement, you don't find any possible real numbers. Especially in measurements, one always finds, as a result, rational numbers. And not only rational numbers, but rational numbers with a finite expansion. You don't find 1/3 when you read the result of your measurement or on display. You find 0.3333 and stop. Okay? With a finite expansion. Then you may say, okay, but it is just an approximation. In principle, you could go forward and make more and more precise experiments and then approximate any real number, but it is not true. So can you consider result of experiments as possible more and more precise approximation of a true real size, okay, true real measure of the physical quantity you are interested in, so the true value of your physical quantity. And the answer is not true. Why? Think of the length of something, the length of an object. Okay? So, for instance, the length of an object is not defined as you enter into the atomic scale. Because inside the atoms there are vibrations and oscillations. So after some, 10, 12 digits, then you are lost. It is meaningless. Okay, and this is the end for now. Now we go to the theory with the next video.